All right, stats, welcome back to another episode of Your Math Teacher Teaches You Stats. So, we are going to be talking about 6.2. Okay, 6.2, get rid of that. And we are talking about the binomial probability distribution. So this is a type of discrete probability distribution. It's called the binomial distribution. So the binomial distribution. Okay, so in the Chapter 6 PDF, this essentially starts on page 14. And first thing we got to do is determine whether a probability experiment is a binomial experiment. So just like we have to check for any type of probability distribution, if we're going to now say more specifically that it's this type of binomial distribution, there's a couple more checks we have to make. And so these are the sort of the conditions for a binomial experiment. And if you kind of remember what that prefix bi means in front of the binomial, it means 2. And that's going to be one of the most important parts of this of these conditions. And I will bring that up in the book, because if you guys are just kind of following along reading in the book, that works. So the first condition here is that the experiment is performed a fixed number of times, and each repetition of the experiment is called a trial. And so the experiment is basically repeated a couple times, how many times we need it to. So just summarize that as there's a repeated fixed number of trials. Okay? Second condition, the trials are independent of each other. Trials are independent. So if you remember back to probability unit, independent. If you think back to the probability unit, independent means that one trial is not going to affect the outcome of the other, right? The probabilities aren't going to affect each other. And then here's that important part I was talking about. For each trial, there are 2 mutually exclusive outcomes. Okay, so there's only 2 outcomes. Okay, and they have to be mutually exclusive, so they can't happen at the same time, right? We can think of binomial experiments in terms of like yes or no, true or false, this or that. Okay, success or failure. The probability of success is the same for each trial. So the probability is the same every time. Probability is the same for each trial. Okay, so those are the conditions. These are the conditions that was supposed to be a star. These are the conditions for a binomial distribution. So, knowing that, let me actually just talk about like one of the most simple binomial experiments we can have. How about like flipping a coin, right? Flipping a coin. Can I repeat that experiment and do it multiple times? Sure, I can flip a coin multiple times. Are the trials independent of each other? Well, if I flip a heads, does that tell me anything about what I'm going to be flipping next? No, they're independent events, okay? Are there only 2 outcomes? Yeah, it's heads, tails, right? Is the probability the same every time I do it? Yeah, it's 50-50 every time, right? 50% chance of heads, 50% chance of tails. That's a great example of a binomial distribution. how we will use this binomial distribution is we can then say, okay, so let's say I'm going to, excuse me, let's say I'm going to flip a coin 20 times. And then I'm going to be interested in the number of heads that I get. Now you might be thinking to yourself, well, the number of heads, that could be anything from 0, 1, 2, 3, 4, 5, 6, all the way up to 20, right? And so is that really a binomial distribution now? But yes, it is, because the outcomes are just, is it a heads or is it not a heads, right? Is it tails? Those are the outcomes we're talking about, right? So we have to kind of look at each individual one and say, in each individual one, are there only two outcomes? And in this case, yes, it's either heads or not heads. And that's usually in a binomial distribution. That's usually how we're going to define our outcomes. It's usually going to be something or not that something, right? And so I could come up with something that like has a lot of different options. Like I could be talking about people's favorite soda, right? And there's a lot of options out there for soda types. But if I just limit the options to just two things, either you like Coca-Cola or you don't, right? So now it's a binomial distribution. It's either yes or no, right? And I can ask a whole bunch of people, and that would be considered my sort of repeated trials. And then I can kind of find out the probability that, 20 out of the 50 people liked Coca-Cola, right? Because it's just like Coca-Cola or not, okay? And that's kind of how we're going to use a lot of these type of things. Okay, so let's take a look. The notation used in a binomial distribution. So what I'm going to talk about here is there's a couple things that we will want to jot down here. So remember that n is going to be the number of trials. The p is going to represent the probability of we're just going to call it a success. Okay? And it's a success in terms of the experiment. So if I'm talking about liking Coca-Cola or not liking Coca-Cola, success would be somebody saying, yes, I like Coca-Cola. It doesn't always have to be a positive thing, though, so this can be sort of strange. In one way, I could be looking at, well, hopefully this doesn't confuse you too much, but how about I'm doing the number of students that failed, like a test or something specific. Well, if that's my experiment, if I want to know how many failed, then every time I got somebody to respond that they failed, that's considered a success for my experiment, if that makes sense. So probability of success just means probability of getting the answer to the question, the one that you're looking at, right? Because we were talking about how we're pretty much going to be talking about it's either going to be something or not something. So the success is how many people said that something, okay? Whatever that something may be. Now, what I do, the book is going to use 1 minus p to simplify some formulas and all that stuff. I'm going to use q to represent the probability of, I'm not going to say failure here, I'm just going to say probability of not a success. Okay, so let's go back to the coin flipping example because that's the most simple example. I'm going to flip a coin 10 times, and every time it's a head, it's going to be considered a success. Okay, and so in that example, P equals 0.5 because the probability of a head is 50%. Q is also 0.5 because it's 50% chance of not getting a head. How about the example of rolling a die? You might be thinking to yourself, well, there's 6 different outcomes, but I can just change that, right? I can say, well, okay, I'm rolling a die, but I'm interested in the number of times I get a 6 on the die. So now my outcomes are I got a 6 or I didn't get a 6, right? So you guys kind of understand now what I mean by binomial distributions, right? One thing or not that thing. So a success would be every time I got a 6. So let's say I roll that die 10 different times, right? And I record the number of 6s. Well, in that case, P would be the probability of success. So what's the probability of getting a 6 on a die? Well, that would be 1 out of 6, right? 1/6. Q would be the probability of not getting a 6, which would be 5/6, right? 5 out of 6, because it's all the rest of the outcomes, okay? All right, good. So let's take a look at some examples, just before I get too far ahead of myself here. Let's determine which of the following probability experiments qualify as binomial experiments. Okay, for those that are binomial experiments, identify the number of trials, the probability of success, probability of failure, and the possible values of a random variable. Okay. Part A. An experiment in which a basketball player who historically makes 80% of his free throws is asked to shoot 3 free throws, and the number of free throws made is recorded. Okay, so in this case, we'll be talking about either make or you miss, right? So, and actually let me go back up to our conditions. So we are checking whether these are binomial distributions. So, or can be treated as binomial distributions. So, first of all, is there a fixed repeated number of trials? Yeah, he's going to do this 3 different times, right? So 3 different times. Are the trials independent? Yes. No, one doesn't affect the other. Are there only 2 outcomes? Make or miss. And is the probability the same each time? Yeah, if he's an 80% free throw shooter, then it's an 80% chance of making it on every single shot. Q would be 20%, right? The probability that he misses. So yes, that is a binomial experiment. Part B. According to a recent Harris poll, 28% of Americans state that chocolate is their favorite flavor of ice cream. Suppose a simple random sample of size 10 is obtained, and the number of Americans who choose chocolate as their favorite ice cream flavor is recorded. Okay, so again, this one can be looked at. Your favorite's chocolate, or it's not. So binomial. What's our n? The number of trials would be 10. The P would be 20.28, 28%, right? What would the Q be? If 28% say chocolate's their favorite, then what percent don't say it's their favorite? Well, that would be 72%, right? And what was the other question? And possible values of the random variable. I didn't do that for part A. So let me just finish part B. What values can it take on? Well, if it's a simple random sample of size 10, what's the possibilities? How many people can say that chocolate is their favorite? Well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, right? And in part A, if the person's taking 3 free throws, what are the possible outcomes? 0, 1, 2, or 3, right? For makes. for the number of makes. Part C, a probability experiment in which 3 cards are drawn from a deck without replacement and the number of aces is recorded. So in one way, we're looking at it's either an ace or not. And there's 3 cards, so that would be our trials. But are the trials independent of each other, and is the probability the same for each trial? So in this case, no. So this is not a binomial experiment. And that's because if there is no replacement, right? This says no replacement. Then every time I take a card out of the deck, it's changing the probability of getting an ace the next time, right? So that's not a binomial experiment, okay? All right, so let's talk now about how we can actually compute these the probabilities of binomial experiments. So I'm going to kind of skip through some of this stuff. We're not going to really go through all the different ways we can do it, like tree diagrams and coming up with, we've done this before, right? So I'm not going to go through all these tree diagrams and come out with all the possibilities and all that stuff. No, we're going to actually figure out a nice simple formula, and it's called the binomial probability distribution function. And it's right there. Okay? So what we're going to do is we are going to take this formula down. So the binomial probability distribution function, or in other words, the binom, I think they just cut it off at that, binom PDF, which is what we will see in our calculator when we get to how to just kind of plug things into our calculator and figure it out. So here's the formula. The probability of a certain value. So let me relate this back to an example. Let's go back to the shooting 3 free throws, because that's kind of what we've been using in chapter 6 so far. Shooting 3 free throws, and we want to know, how many free throws are made. So either make or miss. And let's go with that probability that the person's an 80% free throw shooter. Okay. So what are the possibilities of X? What can X take on? It can take on 0, 1, 2, or 3. Okay. So a typical question would be, they'd set it up. They'd say free throw shooter is 80% free throw shooter. He's shooting 3 free throws. What's the probability that he makes exactly 2 free throws? Okay. So this is what we would do. Our formula is n choose x. So remember, n is the number of trials. Choose, this is a combination, right? So not a permutation, it's just a combination. We have a formula for that in our notes. We also have a way to do that in our calculator. I'll let you guys know that as well. Then what we're going to do is we're going to do P, which is the probability of success, raised to the x, and then Q raised to the y. Okay, and I'm going to explain what we have here. So you might notice mine looks a little different than the books, and that's because I'm using Q instead of 1 minus P, and I'm using y instead of n minus x. So essentially what we have here is this is the number of trials. This is the number of successes we're interested in. The P is the probability of success. I'm kind of running out of room. I've got to work the angles here. Probability of success, or yeah, I'll just write success. Q, remember, is the probability of not success. And then we have these things, and the X is the number. I tried to make the number sign. It didn't really work out. I'm just going to write it out. The number of successes. And Y, this is getting a little messy, is the number of non-successes. Okay. So there's our probability distribution function formula. Let's take a look at our actual example. So let's see if I can leave that on the screen. Yeah. And let's fit in an example here. So we're going to shoot 80% free throw shooter. Shoots 3 free throws. What is the probability of making exactly 2? Okay, so here's what we're going to do. We're essentially finding a binomial distribution function of P of 2. Okay? And what this is how many trials are there? Well, there's 3 trials, so that's 3, choose 2. Okay? And then what's the probability of a success? So what's the probability that you make a shot? In this case, it's 0.8, 80%. And how many do we want to make? 2. And then times, what's the percent of missing? If 0.8's making, 0.2 is missing. And how many do we have to miss? Right? So we have to, because this is either one or the other, we have to have both of these accounted for. So if we're making 2 of them, then we have to miss 1, because we want to know what's the probability of making exactly 2. And so there we've plugged into the formula. Okay, and now what we can do is we can go over to our calculator. There it is. I should probably get rid of that button bind. Anyways, and now we're going to just kind of plug this into our calculator. So if you didn't know this before, there's a quick way to do your combinations and permutations. If you press math and you go over to probability, option 3 is n choose r, and option 2 is n permute r, right? There's your permutations and combinations. So I forgot, you have to write the first number first though. So 3 choose 2. So 3, then I have to go to math and over to this choose 2. Right? So there's my 3 choose 2, and then I'm just going to write 0.8 raised to the 2 and 0.2 raised to the 1. Didn't need to do that, but I will anyway. Hit enter. There's our probability. So the probability that we make exactly 2 is 38.4%. So where's my pen? There we go. So what we got here was 0.384, which is 38.4%. Okay? You might be thinking, well, if the person's an 80% free throw shooter, why is the probability so low? Well, remember that this is exactly 2, right? So if they're an 80% free throw shooter, they're probably going to make all 3, right? The probability of making exactly 3 is going to be a lot more, right? And so, in fact, if we wanted to know that, let me bring the calculator back. It never went away. So if I want to know exactly 3, what am I changing in this formula? I'm going to go up and grab this formula. I'm going to just change what I need to. Well, I don't want to have any misses, so that's going to be 0. And I want to make 3 shots now. And I want to make 3 shots now, so it's there, 3 out of 3, right? Hit enter. That probability is 51.2%. So yeah, that's much higher. Now remember, this is a probability distribution. It's got to add up to 1. So I probably should. Let's keep going with this. Okay. What's another outcome? Well, I could miss 2, and I could make 1. What's the probability of that? Do you think it's going to be higher or lower than 38%? Hopefully it's going to be lower than 38%, right? Because if you're an 80% free throw shooter, you're probably not going to make 1 out of 3 shots. It's a very low probability, almost 1%, a little bit less than 1%, right? 0.96%. And then the last possibility is I miss all 3, which would be crazy. I make none of them, right? So I have 0 out of 3 made, 0 out of 3 successes in this binomial experiment. And that's a very small probability. 0.8% chance, or sorry, okay, back to the last one was 10%. 10%. This one is now less than 1%. Very close to 1% though. Okay, so that's the whole probability distribution. Okay, and if you didn't realize, if we look back at, where was it? Oh, they didn't have it in this section. But anyways, if you look back in your notes, that was the probability. I think I still have that there. That was the probability that we used in section 6.1, right? The 51%, 38%, 10%, 1%, right? They rounded it a little bit. That was the probability distribution they came up with, okay? So it adds up to 1. So that is finding the probabilities in a binomial distribution, okay? The next part of this, here's a nice little review on the mathematical inequality symbols and kind of like how to identify which one to use from a word problem. Good little review there. And the next part we want to talk about here, we're definitely not going to be using tables or anything to find these probability distributions. I don't think you guys want to be looking up all those values. No, we're just going to go right to the technology point, and we are going to look at how to look these things up. So with the, oops, went a little too far. Okay, so with the calculator, there's a couple things we got to mention. So there's binomial. Oops. There's binomial PDF. And binomial PDF is used to find probability of exactly a certain value. So probability of exactly one value, a certain value. Just go with that. And then there's binomial CDF. And that's the probability of less than or equal to a certain value. Okay, so we talked about this before. The binomial PDF is called the binomial probability distribution function. So you input a value, it'll tell you what the probability of that value occurring is. Binomial CDF is the binomial cumulative distribution function. So it kind of adds all the other probabilities up as you go. And so it gives us a probability of getting, like in our example, if we were doing binomial CDF of 2 free throws, it would be the probability of getting 2 or less free throws. Okay, so it's going to add all those probabilities up together for you. Okay, so that's the difference between binomial PDF, binomial CDF. Okay, PDF is for one individual value. CDF is cumulative. Okay, so less than or equal to. So let's take a look at this book example. According to the Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what is the probability that A, exactly 10 favor the death penalty, B, no more than 6 favor the death penalty? Okay, so this is example 5. And when we do, like, I could just pick up my calculator, type in everything I need, and get the answer. I don't want to just write the answer down, though, on the paper, because that just kind of loses all hope for partial credit or whatever it may be. So I'm going to show at least what I'm plugging in. So first, let's talk about where to find this stuff. So back to the calculator. Clear all that out. Okay. Back to the calculator. We have our distribution button is above the vars, the variables button. So we're going to press second, which just came up there in red, and then vars, which is right next to clear. Okay, so it just came up in red there. So press second, vars. That brings us to all the different distributions. And we're going to use this feature on the calculator a lot, like for the rest of the year, okay? All the time. So here are several different distributions, right? There's normal distributions, there's inverse distributions, there's t-distributions, there's chi-squared distributions, there's all these different, but as you can see here, there's a binomial distribution. So we're going to choose this, and all of a sudden we get this screen where we're supposed to input all of this stuff. So if we go back to this question, it says a simple random sample of 15 adults. So I'm going to identify that my n is equal to 15. And then I'm going to identify that my P is equal to, what is the probability that 10 favor the death penalty? So what was the percentage of favoring? Percentage of favoring was 65%. So that's 0.65. And I know you don't have to type it into your calculator, but I also like to just kind of write, well, that means Q equals 0.35, right? And then what are we interested in? Exactly 10, so X equals 10. Those are the three things we're going to plug in, and I'm going to even write down which one I used, right? Because if I accidentally used the wrong one, but identified all the right values, maybe I get some partial credit here or there, right? It's all good stuff. So let's go ahead and figure this out. Number of trials is 15. Probability of success is 0.65. We want to know exactly 10. That's what will show up on your calculator. You just hit enter, and there's our probability. Okay? So rounding, we get about 21.2%. So this one came out to be 21.2%. This is part A. Okay, part B. Part B, no more than 6 favor the death penalty. So what does no more than 6 mean? It means 6 or less. And so that is just our regular binomial CDF. So we're going to go to binom CDF on our calculator. So I'm going to press second vars, and I like to just go up because I think it's quicker to get there. Yeah, probably. Right there, binomial CDF. Number of trials is 15. Probability of success is 0.65. And the X value in this case is, we want to know no more than 6. So we are interested in less than or equal to 6. Remember that CDF will always give you less than or equal to. So if we want to know the other side of that, we have to take the complement. Remember the other probability, right? So like P and Q, that type. So 6. There we go. Hit that. And we get, oops, didn't need to do that. So N was 15, P was 0.65, X was 6, and we got about 4.2%. Okay? So there is our binomial distributions. PDF, CDF. PDF is the exact value. CDF is a cumulative distribution, and the next part, I think we just have like one more part to go over here. This might be going a little long, but I think we can finish this up. So the next part is the mean and standard deviation, and for that, there's going to be two formulas to use. So the mean of a binomial distribution is going to be n times p. Okay, so think of it. Let's use the 80% free throw shooter. If I'm going to ask an 80% free throw shooter to shoot let's say 35 free throws. On average, how many do we expect the person to make? Well, there's 35 free throws, so n would be 35, and the probability of each one is 80%, so 0.8. All you do is 35 times 0.8. Okay? So you just multiply the number of trials times the probability. Okay? For standard deviation, of a binomial distribution, the formula is the square root of n times p times q. Okay, so it's just, you take the number of trials. So in that same example, if 35 free throws, I'd take 35, and then I'd multiply it by 0.8, probability of making a free throw. I'd also multiply it by 0.2, probability of missing a free throw, and then I would take the square root of that number, and that would give us the standard deviation. Okay, so there's those two free throws there. Two formulas for mean and standard deviation. Again, we're not going to go into graphing the binomial distributions. Just remember, it is a discrete distribution, so it looks like that weird little, just a bunch of points in it. You know, we can talk about skewness and what all that, but it's not continuous. It's just a bunch of points, right? And yeah, other than that, here at the bottom of, what PDF page is this? At the bottom of page 24, it has, again, those the calculator steps here, talking about how to do those. And yeah, that is it for 6.2. All right, so you guys got a couple of practice problems to do in 6.2, and I'll see you guys later.